we're going to talk a little bit about 1584, and for some, 1584 changes occurred in 2018, so it's kind of older news, but what we're seeing is customers coming to us now saying, hey, we've had changes to our arc flash values based on reviews we've done for 1584 and the new processes. Denise is going to talk about some of those changes you may be seeing since the changes have taken place, and overall circuit breaker condition and how that relates to arc flash safety. Again, questions this morning or this afternoon, if you would, post those in the Q&A. I'll watch for questions and then notify Denise when these changes, when the questions come up. And then if we get a lot, we'll table those toward the end. So with that, Denise, thanks for today. Thanks for your time. And thank you everybody for joining us. With Denise.
Thank you. So as Justin said, we're going to talk a little bit about circuit breaker condition and how it affects arc flash safety. As you all know, Arc Flash 101, electricity leaves its intended path, either goes phase to phase, phase to ground, and that's how an arc flash occurs. The implications of breaker maintenance on arc flash situations can be very severe. So that's why we're talking about this and hopefully spreading a little bit of awareness about how those components affect the people that are standing in front of the cell and dealing with the breakers. I just wanted to touch a little bit on some common causes of arc flash that don't have anything to do with maintenance, but it's a concern nonetheless. These four things are very common causes of arc flash situations. As we're doing maintenance, the pictures there are of a Saatchi breaker. That little square rectangle part right there is a lifting device for a Saatchi breaker. It was at the very end of the day. The crew was trying to wrap up quickly, and they set that lifting device on the back of the breaker, bridging phase B and phase C, and did not notice it when they installed it in the cubicle. So it turned into an arc flash incident as a consequence of doing maintenance. So while we're talking about breakers and poorly maintained breakers, it's also important to remember that there is some things that can happen while maintenance is going on, and making sure that peer review is happening and that we're really being careful while we're racking breakers in, racking breakers out, and doing the maintenance portion. So that's kind of my throw in for while you're doing maintenance, please everyone be careful. Common causes of arc flash that are related to maintenance. Loose connections, obviously. Water intrusion. Water intrusion cannot just be an active leak. It might be an environmental situation where there's condensation, there's water in a trough below a substation that's evaporating continually onto the gear. So water intrusion takes several different facets when combined with electricity. So it's important to remember that not just an active leak can cause an issue. Poor environment is a very large portion that affects maintenance and breaker maintenance cycles. If you're in an environment where there's a lot of particulate matter, that environment is going to affect your maintenance schedule and also affect the condition of the breaker over time. Worn, failed, or damaged insulation is a situation, and then obviously improperly maintained or maintained breakers that the maintenance isn't happening frequently enough can cause arc flash situations to happen. So a lot of breaker issues can be found during just inspections. So the picture on the left, if you pull a panel off and everything is rusted, and you can see that all the metal at the bottom of the gear is rusted, the supports are rusted, that is an indication that, despite testing, you have a maintenance situation on your hand that could lead to an arc flash situation. the continual rise and fall of water and the deposit of rust and contaminants makes this a highly likely area for an arc flash situation to occur. I'm sure you've all seen loose connection situations. That's a maintenance concern. You know, when you're maintaining, especially molded case and insulated case breakers, that at some point, you know, those cable connections are checked. It's especially important, you know, between 6 months and a year after a new installation to make sure that those initial installation connections are still tight and those are backed off and retorqued to verify that nothing loosened after everything settled and sat there and had that 60 hertz hum going through it, that you don't end up with any loose connections. The lower picture is damaged insulation. Obviously your substructure and inspection of your substructure goes along hand in hand with your circuit breaker maintenance. So taking the time to take outages on a regular basis so that you can inspect the structure as well as your breakers can help prevent an arc flash situation. So the maintenance goes to not just the breakers, but your substructure as well. So this is an interesting situation that was definitely a maintenance inspection driven arc fault. If you can see, those 3 horizontal bars are the bus, the line bus that goes through the gear. And upon initial installation, there was supposed to be a piece of insulation on the end of each bus bar. Well, for whatever reason, phase A and phase B did not have that insulation installed. And over the time, as the gear was there, no one noticed that insulation was not there, despite this gear having been inspected. They had a severe wind event, and the wind was strong enough to flex the center of the side panel in toward the bus. And the side panel breached the distance between the arc flash distance between the bus and the panel. And you had a phase to ground beginning fault that turned into a phase to phase fault. And you can see the melted structure above, in addition to the hole welded in the side. So that maintenance component, when you're not only taking care of circuit breakers, but looking at the gear itself, is important to make sure that even initial installation problems are caught down the road so that something like this doesn't happen. So I briefly discussed this. So the maintenance and environmental concerns with circuit breakers, when you don't maintain a breaker, there is an operational disadvantage that breaker is in. When a breaker stays in a closed position for an extended period of time without being maintained or cycled, it is less likely to operate in the expected way. So my boss, Finley Ledbetter, likes to use the example that if you stood with your palms pressed together in front of you as hard as you could for 5 years, and then tried to open your hands as quickly as possible, it probably wouldn't happen like you expected it. So that is a situational breaker maintenance concern with lack of operation. The next component is lack of lubrication. So most lubricants that are on the market now that are recommended by the OEMs and the NETA 70B, the NFPA 70B and the NETA MTS recommend that equipment be lubricated every 3 to 5 years, unless it's in an environment that requires it more quickly. The reason for that is the components inside the lubricant in the lubricant products that we use are only good for 3 to 5 years. And the 3 to 5 years is in perfect conditions. So if you have an area where those conditions are not perfect, that lubrication is not going to perform as intended over extended time periods and in poor environments. So really thinking about the lubrication and how you're maintaining your equipment is really important to your breaker correct operation. Okay, so that's only one side of your equipment, and it helps to think of breakers. Breakers are mechanical devices that just happen to carry electricity, and you have to think about your equipment in that mechanical mindset before you think about it in the electrical mindset. Okay. So the other components of the concerns for breakers, like we talked about, are atmospheric conditions. So is it in a moist atmosphere? Are you in a water treatment facility where there is a lot of chemical component in the air, hydrogen sulfide, those kind of things that break down components in switchgear? Are you in an area where you have a lot of dust, whether that be flour dust, grain dust, metallic dust, uh, carbon, coal, any of those things? That's going to impact the ability for the breaker to do its job, and also impact the breaker when it has to interrupt under a fault. We talked about moisture a little bit, whether that be an active moisture leak or whether the moisture is a result of the environment, whether your heater strips are not on, whether you have a heater strip located in an area that can potentially cause damage to the breaker. I saw a failure where heater strips were mounted on the side of the cells very close to the GPO3 barriers of the breaker instead of down below that. The heater damaged the GPO3 to the extent that the voltage was able to jump from the pole piece to ground through that deteriorated GPO3. So that's a concern as well when you're working with environment and location. And then temperature is the last one. So circuit breakers that are in very high temperature environments will have their lubricant come to the end of its working life a lot sooner than equipment that's in a more climate controlled environment. The opposite happens when the temperature is very, very cold. You have grease products that are in the breaker as lubricants tend to get thicker and stiffer. So you might not have a breaker open physically as quickly as it should when it's in a very, very cold environment. So it's important to, assess your equipment and look at how your system is, and how are we going to make sure that all of these things can make sure our breaker is working to the best of its ability, so that when it goes to open, then we don't have an arc flash or a potential arc flash situation.
Hey, Denise,
Uh-huh.
while on this point of environment, and you just spoke to this exact question to a degree, and I just want to know more. The question is, what kind of environments would reduce lubrication life? And you're talking about temperature just now specifically for lubrication. Are there other things related to that?
Yes. So temperature really affects the lubrication. What you have in the environment. So if you have gases in the environment that are detrimental to your breaker and the lubricant properties of your lubricants, that will contribute. Dust, any kind of debris or dust that can get into the cabinets onto the breaker is going to cause an issue. I did some work at a baby food plant that happened to process baby cereal, and baby cereal is ground extremely fine, and any humidity in the cubicle caused that fine flour to turn to cement, and caused a cement-like buildup on the hinges and reduced the ability of the breaker to open. So, and then also the lubricant gets contaminated with that environmental particle that's there. So if it's a metallic particle, if it's coal dust, like I said, grain dust, sugar, any of those things that contaminate the breaker also affect the lubricant properties that are in the breaker, that then can affect how well the breaker opens.
Great.
Does that answer your question?
Yeah, I think, in fact, Jay says, thank you for the additional clarification. That's great. One
Right.
more for you, though.
Sure.
You mentioned this when you were talking. What is a GP003?
Oh,
GPO.
GPO3. Oh, sorry, I used the technical term. So on a circuit breaker, many circuit breakers have barriers made out of a red resin material that's impregnated with fiberglass. And that red resin material that you see in barriers between phases, it's on all different voltages of breakers. That red product is called GPO3. The light green product that you see a lot of times in higher voltage applications is called G10. And that also has the insulating properties that are used in electrical applications to stop phase-to-phase involvement in circuit breakers. So when breakers open, that's an extra barrier in between the arc chutes to keep ionized air from going phase to phase. And so that has pretty decent non-flammable characteristics and pretty good insulating characteristics. You'll see that a lot in the back of gear as bus supports, as supports for current transformers or potential transformers. That they use that insulating material. They use L shapes of it for supports. And racking supports for copper bus. So
All
that's
right.
what GPO3 is.
Cool. Very good. Rick says thank you for that answer. And we're
Sure.
clear. Thank you.
Sure. I tend to use the technical terms because I buy it and use it, so I apologize. Okay, some consequences that can happen with a lack of maintenance on a breaker. And the two bottom ones are pretty close in the severity. So it was kind of a toss up on which to put first. But I'm going to start at the bottom. So our first problem that happens with a breaker that hasn't been maintained is that it doesn't trip as expected. So it gets a signal, whatever trip unit is on the breaker sends the proper, whether it's a signal from a solid state trip unit from the CTs to the actuator, whether it's an electromechanical trip unit, whether it's a thermomagnetic trip unit in a molded case breaker. The first problem with lack of maintenance is your breaker just doesn't trip. So the problem with the failure to trip situation is you can overstress the cables and the bus longer than the equipment was designed to be stressed for. And if your breaker doesn't trip, hopefully the breaker upstream or the fuses or the device upstream is the thing that does trip. But the consequence with that is you have a larger outage. You didn't anticipate that all of that was going to happen. Well, if a breaker is operating with a trip unit, you didn't anticipate that either. But your cascading event gets much larger when a breaker doesn't trip. So instead of one feeder tripping one motor control center, you might have the main trip and take out half of a substation, an entire process at a facility. So that can lead to equipment damage. If a milling machine stops in the middle of what it's doing, you're going to have product damage, milling machine damage, tool damage. All of those things can happen when a main trips instead of a feeder. The next consequence is a delayed trip, which is almost the same as a failure to trip. You have an extended stress on the cables, the bus, and that piece of equipment itself. The reason I have delayed trip a little bit above failure to trip is when that breaker does trip and you've now had your fault at a longer than anticipated time, your available arc energy is more. So when the breaker opens, you have a greater risk of physical damage to that breaker. So instead of it tripping at 3,000 amps that the trip unit was set at, the fault escalates. And because it didn't trip as quickly it was supposed to, because it wasn't lubricated properly, now your fault is 8,000 amps or 10,000 amps. So that's a very different event for the circuit breaker and for the contacts in the circuit breaker to deal with. So it's much harder on your equipment and can cause damage to your equipment because the breaker isn't opening quickly enough. So all of those design features of a circuit breaker are based on its capabilities of interrupting and how quickly you can interrupt a fault. So that's a potential problem with a delayed trip. At least at that point, the breaker has tripped. So you are isolated, hopefully, to that one area that the length of the fault wasn't long enough for then the main to catch it as well. This is especially hard with ground fault and instantaneous faults. Sometimes an instantaneous fault escalates so fast that if a feeder breaker doesn't trip quickly enough, the main will pick it up and trip as well. So you get into that same situation as the feeder failed to trip and now the main is interrupting as well. The very most dangerous one that is directly related to breaker maintenance is if a breaker partially trips. So if the trip unit gets the signal, it tells the breaker that there's a problem, the actuator gets actuated, the trip bar gets hit, and the breaker only partially opens, you run the risk of the contacts still being close enough that you have not bridged the gap that voltage can jump, or that the arc doesn't extinguish because your contacts are very close. And now you have a situation where you have the generation of ionized air. And once the ionized air that's generated at that particular point goes to another phase or phase to ground, now you have a full arc flash event. And that can happen very easily when a breaker does not trip all the way. It can happen at any voltage class, so it doesn't have to be at a medium voltage level. If a breaker, even a 480 breaker, trips and the gap is only 1/8 of an inch or 1/16 of an inch, you're going to have a situation where that arc does not extinguish when the phase is open. And now you get into that ionized air arc flash situation. So at that point, now you have, damage to equipment, potential damage to personnel, if anyone is there, downtime, and it's not quickly recoverable, like a delayed trip or a failure to trip. So that's the most severe consequence that can happen as a result of a partial trip on a breaker. I see someone has a question. Is it pertain to this?
Yeah, so does that hold true also for vacuum bottles?
Yes. Well, yes and no. So I was involved in a situation, this is a real life situation, where a customer had continued failure of their vacuum interrupters on their breakers. Originally, they were working with the manufacturer. They thought there was a bad batch. No one could figure out what happened or what was happening, why the bottles failed. If you lose vacuum in an interrupter and that breaker opens in a fault situation, the gap between the contacts inside that interrupter is not sufficient to break the circuit, and you will have a full arcing event. The breaker that I'm talking about, they got struck by lightning, and they had lost vacuum in one of their interrupters on a power vac. And the breaker opened, but because there was no vacuum, the gap was only 5/16 of an inch or whatever the gap was on that particular interrupter, and the entire breaker burned down. I don't know if you're familiar with a power vac, but it's got the orange insulation completely on each pole. The entire insulation was burned and gone. It welded a hole through the front cover of the breaker. It welded a hole in the side of the cubicle, and turned into an extreme arc flash fire event. What it turned out to be was all the years that they were having the breakers tested, this was at a utility, so they never shut down the gear. Well, because of this event, the gear had to be shut down to be repaired. And when we got in the back and got the covers off, we found that a connection had not been crimped at time of installation. So all the years of spiking faults on that loose connection on the cable was causing the interrupters to fail. And that caused then the cascade of events. So if you maintain breakers and you check your interrupters and you make sure that the integrity is good, either with the standard methods of using, a high potential test set to do vacuum integrity, or if you use the MAC test set to get a more quantitative value on your vacuum interrupters, that gets you a long way toward avoiding a complete meltdown of your breaker, because it under fault, it will not interrupt that. So did that answer your question? If a vacuum interrupter is in good shape, then it's going to interrupt and everything is going to be fine. If your vacuum interrupter is not in good condition, and you have either close to the end of life, where you have too many molecules of contaminant in that interrupter, or the interrupter has already failed, then you can have that issue with the partial trip. In vacuum, it doesn't matter. The gap is so small that as long as the breaker opens, it's not going to be an issue.
I just want to point out too, you mentioned MAC test, and that's a whole nother presentation. Completely.
Right. But that's a quantitative way of testing your interrupters.
Yeah. But we have presentations for that.
Right.
And Finley has talked through, and if anybody wants that, shoot me a note. I'll make sure you get the MAC test presentation as well. Thank you, Denise. Oh, one more thing too. You mentioned low voltage breakers. You know, bottles are typically on your high voltage breakers or your medium voltage. But you know, I see incidents of arc flash occurring more so on low voltage, and people seem to dismiss those a little bit in general. You know, do you see that and hear that too?
Well, it's 100% science and physics. Usually incident energy numbers are higher at 480 volt equipment than they are at medium voltage equipment. Medium voltage equipment has relaying that operates quicker than low voltage trip units do. Usually they're fed through, there's some impedance with cables and distance applications, you know, for medium voltage breakers. The other thing with a medium voltage breaker is the gap between the contacts is a lot bigger. So you have all of those components that make incident energy lower most of the time on medium voltage gear than it is on 480 gear. I will tell you that if you have a 2500 kVA transformer that's a 15 kV to 480 277, and you have a 3000 amp main breaker, that main breaker will always be over 40 calories on the line side of that breaker. 100% always. So it's very important to, you know, take those labels and your awareness of the potential consequences at 480 very seriously. You know, it's very common to see labeling on medium voltage gear, you know, at less than 10 calories. Well, you have to remember that equipment breaks apart between 12 and 15 calories. So knowing that when you look at that low voltage breaker and it's a 20 calorie arc flash incident energy, that there is a higher consequence of more catastrophic damage at that lower level. Okay. So yeah, and now when we get to the 1584, we're going to talk about the 240 volt component to all of this. So you know, considering that. So are we good on the partial trip? Okay. So now we're going to talk a little bit about trip times in relationship to arc flash. And this directly goes to breaker maintenance and breaker condition. So this is a standard breaker trip curve. If you've never seen one, it shows long time, all the long time bands and instantaneous bands on this particular curve for a standard solid state trip unit. This is, and I wanted to put this on here so if you've never seen one, this is from a coordination study that shows multiple devices all layered on the same drawing so that coordination can be properly made between feeder breakers, main breakers, fuses, primary breakers, and all the components that feed that circuit. And so I like to include this so you can see that the selection of time bands is not random in your coordination study. You know, it directly relates to all of the components in your system, and that's how the settings are generated by what substructure, what fuses, what equipment is there, and then the availability of changing settings and getting everything so that if there is a fault, that that items open in the proper order, so you don't have a whole substation, single-headed substation going offline because you had a little motor on the roof lock up and your breaker that was supposed to shut that off didn't trip. So that's just the whole coordination study view. So when we talk about trip times and incident energy as related to breaker maintenance, this is an arc flash evaluation report. So standard report that was done by our engineering service group. And I'm going to zoom in on the main breaker. So this is the main breaker from that system. And these are all the settings for the trip unit and what method was used. And you can see that this was calculated using the 2018 formulas for IEEE 1584. You can see that this breaker has a trip time delay of 0.143 seconds. Okay, so that is the 0.1 setting minimum, whichever trip unit happens to be on this breaker, that is what the setting is for instantaneous. And you can see that the incident energy at that breaker is 2.13 calories. So if the breaker is well maintained, if the breaker is lubricated, if all of those components are correct, you would anticipate this breaker to trip in 0.143 seconds, and that your arc flash boundary is 22 inches and it's 2 calories. So the electrician or technician that's approaching that cell and looking at that label, it's going to tell them that they need to wear either 4 or 8 calorie PPE. It's going to tell them to have a face shield on, safety glasses, earplugs, the proper shirt, usually an 8 calorie shirt because that's what you should wear. And the technician or the electrician thinks that they are completely protected. Okay. This exact breaker, same main breaker, 1536, if that trip delay time extends to 2 seconds instead of 0.143 seconds, you now have an arc flash boundary of 112 inches instead of 22. And your incident energy is now 29 calories, almost 30 calories. So your technician or electrician that's standing in front of that gear that is anticipating a 2-calorie event if something happens is now standing in front of an almost 30-calorie event wearing 8-calorie PPE. So that is why it's super important that to understand that a lack of maintenance directly impacts arc flash situations. Now we have crossed the line. If there is an arc flash, it's no longer a 2-calorie arc flash. It's a 30-calorie arc flash. We've crossed the line into equipment failure, debris, slinging bolts, doors flying open, all of those things happening, and no one anticipated it because they went by the label. So just that small amount of time on even a delay, when I talked about a delayed trip, can cause a serious situation to the equipment itself, because now your incident energy availability is so much higher. The fault is ramping up exponentially. The incident available current is ramping up exponentially during a fault. It's not linear. And you've crossed into a very dangerous situation in a very short amount of time. So I wanted to sort of give you the view of the exact same breaker with just a change in trip delay time. And then you can imagine if the breaker partially opened and you had a situation going on where then that incident energy would end up even higher. Now we're going to talk about the breaker condition and evaluating labels. We're going to talk about the 1584. So it's really important, when your technicians are standing in front of the label and they're looking at that arc flash boundary of 89 inches and what the incident energy is, to keep in mind, how was that equipment maintained? Has it ever been maintained? Has it been installed for 25 years and no one has ever opened up the door? So that's really important. This is a standard arc flash hazard label This one was generated in 2014. I have another label to show you that was generated in 2018, and we're going to talk about concerns about labels and how to read them when we get to the 1584 section. So this is a label that was generated in 2018, and this particular label will have taken into account the newer version of the 1584 formulas, calculations, and components for calculation. So having your staff pay attention to the date that the label was created is also really, really important in determining their hazard when they're standing in front of it, along with the maintenance concerns. So I see there's a question. This might be a good time to stop. Yes?
Yeah, so the question is, what maintenance can you do to a molded case circuit breaker to take credit for the manufacturer trip times in an arc flash study?
So you can make sure that that breaker gets operated. Depending on the amperage size, and this gets into that walking the line. A lot of customers of ours have a cutoff, and they say, okay, if a breaker is 400 amps or above, where there's a higher hazard of injury or damage to equipment, we're going to pull that breaker and we're going to high current test that breaker, or secondary test that breaker if it happens to have a solid state trip unit on it, to make sure that that breaker is operating in the time and as expected. A lot of lower amperage molded case breakers, the incident energy is so low that then there isn't that concern for equipment and safety. So the dollar value of the breaker is not justifiable to pull it out, test it, and put it back in. You also have to weigh the ability to pull molded case breakers in and out often. A lot of gear has the bolts that bolt the breaker to, like if it's in a motor control center panel and the line side is bolted directly to the bus, those threaded holes are just directly threaded into the copper, and repeated removal and installation can cause issues down the road. So you have to weigh what is the incident energy at that particular breaker, what is the cost of replacing the breaker, and what is the potential that I can't get the breaker reinstalled after pulling it out the 10th time. So if you're only maintaining breakers every 5 years, that's 50 years. But if an inexperienced electrician misthreads that bolt, now you have a situation where it's hard to put the breaker back in the proper way and get it bolted back into the motor control center. So that's very much a financial decision, oftentimes based on the incident energy. But the answer would be test the breaker. That would be the answer, is pull the breaker out, test the breaker, and make sure that it works. If you have insulated case breakers, those ones are usually bolted in, and so that's less hazardous to remove and reinstall because you're not threading into copper bus. But that would be the way to verify, is to high current test that breaker. Okay.
Thank you.
All right, you can secondary test breakers. I do recommend, if you secondary test breakers, that the testing group actually closes the breaker to verify that the actuator is actually tripping it. So just testing the trip unit and not verifying that the breaker operates is not doing, more of a complete component test. Usually, I've been doing this for 33 years, and I don't see a lot of CT or Rogowski coil failures in molded case breakers and insulated case breakers to justify, testing the CTs in any other way besides using a meter and verifying that the resistance is the same on all three. You can get into dangerous situations with doing resistance, checking the resistance on CTs. If the person doing the test isn't careful, they can damage the CT, because those breaker CTs are not the same caliber as metering CTs that get tested on a regular basis. So just keep in mind to test the action of the actuator if you're going to secondary test. Okay. All right.
All right, thank you.
Okay, so 2018 IEEE came forward with a lot of changes in the calculations for incident energy and arc flash distances. So the previous revisions to the formula had happened in 2002. So over 16 years, they looked at the coefficients that they were using for cubicle size and decided that they were still seeing arc flash incidents and maybe unexpected arc flash incidents. So they set to determine formulas that would take into account the cabinet size, the electrode configuration, and then they also found that they needed to add a consideration for equipment 240 and below. So prior to 2018, there was no arc flash labeling requirement or calculations for equipment at that voltage class and below. And over 16 years, when working with the NFPA, they saw that arc flash incidents were happening. So that there was a determination that because arc flash incidents were happening where people were getting injured on equipment 240 volts and below, that now that should be a piece of equipment that should be evaluated and potential labels created for equipment below 240 or 240 and below. There was some calculation being done for currents over 2000 amps at a 240 volt level, but they expanded those calculations in 2018 to capture areas where personnel might be in danger and that were not being considered previously. So that's the first really big change on lower voltage equipment. In your facilities, it's definitely a thing to evaluate. If you have very low amperage breakers at 220 volts, 30 amps, 40 amps, chances are your arc flash is not going to exceed anything, that is concern other than normal PPE. But when you start getting into larger amperage breakers at that lower voltage rate, you really might consider having that calculated to make sure that everyone is protected, when they're standing in front of it and operating that equipment. Arc flashes, unless there's impending failure, happen when you're racking a breaker in, racking a breaker out, closing a breaker, and tripping a breaker. Those are normally the times that an arc flash incident happens, unless Frank left his crescent wrench in the gear 6 months ago and it finally vibrated over and fell across the back of the gear. That's a whole different topic. But as far as evaluation,
And that's related to condition of the breaker, right?
Yeah.
I mean, the arc flashes also happen quite frequently when we're using underrated tools or equipment,
Yeah.
and them, or there's human as they're
human
touching.
error, right. But if equipment's not, if there's damage to insulation, if your insulation system is failing because your equipment is in a poor environment, you haven't been inspecting it, you don't know that the insulation is failing, then you can have an arc flash incident, even at 240 volts. So the second component of the change that is probably pretty equal to the next one is a change from standard size. And the biggest place that this is obvious is prior to 2018, there was a standard of coefficient that every cubicle was calculated at a volume of 20 inches by 20 inches by 20 inches. Okay, so that was just it. They had a coefficient, that's what they used for volume, and everything was based on that. Well, they decided that there are a lot of shallow cabinet applications that pose a very large hazard to people and to companies, that the arc flash, the incident available energy is very high. So they have now factors in there to take into account whether your cabinet is shallow versus typical, and alternate sizing is included in calculations. So if you're going from the old calculation of a 20 by 20 by 20 cabinet to a Magnablast cabinet that is 36 by 42 by 75, you're going to have probably a little bit lower incident available energy as far as blast goes. Your distance might be a little bit further because there's more area, more volume for that arc flash to go. It doesn't all come out at you. Some of it goes toward the back. Conversely, if you have a disconnect that is 38 calories and it's only 8 inches deep, if that label were to be recalculated, it's very likely that that would exceed the 40 calorie and make it unsafe to operate. So training your people to know that cabinet size can affect your existing label is really, really important. Along with, if the breaker was not maintained, then that's another component to say, okay, I have the report, this breaker wasn't maintained for 15 years. This label doesn't mean anything. Okay. So that's a very, very important thing. Now, I will tell you, in both the 2018 and NFPA 70E and the 2021 NFPA 70E, they have not made it a requirement for labels to be recalculated. So the standard says that your arc flash labels and your study must be reviewed every 5 years. It must be documented that it's reviewed, and any significant changes that were made to the system, those labels must be recalculated. But they have not come forward and said, hey, we made this change in 2018 to the calculations. Everybody that had their stuff done before that, you have to redo your labels. That has not happened yet. But it's important for you and your staff to know that the number on the label could be different based on the size of the cabinet. Okay, so that's kind of the deal there. One thing I want to say about labels and your personnel, there are 5 components to judging the accuracy of the information on the label. So was the equipment chosen properly? Was it installed properly? Unlike that one that flashed over, it wasn't installed properly. Was the equipment maintained properly? Are all the doors and bolts installed? And are there any signs of impending failure? If those 5 things cannot be answered in a true fashion, the information on that label is not correct. Okay, so that goes to that time on if the breaker trips in 0.14 seconds versus 2 seconds, that goes directly to that. I see there's a question.
Sure, yeah. This question is regarding IEEE 1584 2018 enclosure size. What size of enclosure is modeled while the draw out type circuit breaker is installed? The breaker takes up most of the box space with little room around each side.
They still use the total volume of the cell. They still use the total volume of the cell because they're looking, they can't predict if an arc flash happens while a breaker is being racked in or out, where that breaker is in the process. So you can't say the breaker is always 75% in the cell versus 25% inside the cell versus 100% inside the cell. So they go with the volume of the cell. That's just, they had to pick a path, and that's the path they chose. So, it's too hard to model for every single different kind of circuit breaker. The formulas, if you've ever looked at the formulas for calculating available incident energy, it's back to, calculus and all of that. And to add a different coefficient for an AK25 versus a DS416 versus a K1600 versus, they just can't add all of those volumetric calculations. It was hard enough to come up with sizing, different sizing components away from the 20 by 20 by 20. So it takes into account the volume of the cell, if that helps.
Yep, thank you.
So the third change in IEEE 1584 is now the calculations take into account the direction of and type of conductor that's in the cell. So they realize that every one of these instances creates a different dynamic with the available incident energy. So now they've been able to add that if your breaker cell has vertical bus like a Magnablast is different than if a breaker has horizontal bus like an AK-75 or a Westinghouse DH or a PowerVac. Those are all horizontal bus in a metal box or enclosure. They found that because in open air, air helps dissipate arc flash events. So they have added different calculations for vertical conductors and horizontal conductors in air because those risks are lower in open air than they are inside an enclosure. So they also added a component where there's an insulating barrier to the mix. So insulating barriers versus open transition, in equipment, where an arc flash incident can get contained better in a situation where there's insulating barriers versus not. So they were able to add all of these components to the calculations to help the labeling be more correct and more accurate. We want to make sure that everyone is wearing the proper PPE. It's always my approach to size up. I'm not, if I'm standing in front of something that's 7 calories, I'm not counting on my 8-calorie equipment. Even if the equipment was maintained, I'm going to err on the side of caution and wear something more robust because it's so close to that 7 calories. Okay. So any question about conductors and electrodes? Okay, the field considerations regarding your labels. Always remember that the lack of maintenance of your equipment will generally increase your hazard. I put may, it's going to increase your hazard. The unfavorable environment may increase the hazard. On this unfavorable environment, keep in mind when you're doing things in your plants, it sounds really easy to tell the janitor, hey, go sweep up that substation. There's a lot of dust on the floor. I don't want the dust in that substation. Go take a broom and go take care of that. That act of creating an unfavorable environment can cause an arc flash explosion. So being cognizant of what an unfavorable environment is really important in and above the actual day-to-day presence of chemicals, contaminants, air pollution, all of that stuff. So keep that in mind, on your what's going on in your plant. And then the last one, considering, the field consideration above the maintenance one is, having your employees look at the date on the label and have a discussion when you're doing your JHA or JSA, whichever you call your job planning form, on what considerations you're going to give to the ratings on that label. And is that label still accurate, or do we have to make additional plans or choose different PPE based on the changes that have happened with 1584? So the same thing applies to your 240 volt equipment and below, your 240, 208. You generally don't see quite as severe arc flash situations on 120, mostly because the amperage is usually pretty low. But you can have some significant amperage equipment at 240 or 208. So keeping that in mind, that you might want to consider, if you have a high amperage breaker at that lower level, that might have an increased hazard and something that you need to be concerned about. I see a question.
Question in here saying for draw out circuit breakers or switchboards, what electrode configuration should be studied? Seems like all three could be found inside these types of enclosures.
Yep, all of them can be found. It just depends on the type of equipment. So when you get, if you have to do an updated label, that actual gear will be taken into account, like when the data collection happens, then that particular type of gear, the person doing the study will be able to determine, is that gear, a vertical in an enclosed cabinet, is it horizontal in an enclosed cabinet, all those things, and that will be a part of the automatically of the calculation now that it's after 2018. So if you feel that you have a substation that your labeling and your values are very high and you're approaching that 40 calorie level, that might be a worthwhile investment to have some of those labels recalculated so that you're sure that your staff is using the proper tools and the proper PPE to interact with that equipment. So it's not as much of a concern on your end as it is just on a calculation label end. If you err on the side of, if this is 20 calories and you have your staff wear 40 calorie suits, you're most likely going to be covered. The changes that I've seen in recalculations of labels have not doubled the availability. It goes up the most in shallow 8-inch deep and 12-inch deep cabinets is where it goes up the most.
Is there a particular amperage level that's a good rule of thumb to be concerned about with high incident energy?
At the 480 level, everything. At the 240 level and below, I would probably think I've not done that calculation, so I'm just surmising, but I would probably think it's somewhere at the 400 amp level is where that would probably start to cross that line. But I would have to have somebody put that into SKM and see what we have, and see if at 240, that anything below 400 would exceed an incident energy level that would be, potentially hazardous, to personnel.
I've got one more that came in, Denise. And, if this needs tabled toward the end, we're coming up on our hour here, but
I only have one more slide, so.
Okay, oh, great. Now I'll go ahead and roll with this then. For arc flash labels, the label has a working distance and level PPE at that working distance. It also has the arc flash boundary distance. How do you determine the level of PPE entering the arc flash boundary, but not near the working distance?
Okay, so the reason that there's a boundary, an arc flash boundary, is at that boundary distance, like the one that was 112 inches that I showed. At that level, without PPE, you are at risk of a second degree burn. Okay, with no PPE. So that arc flash boundary is the indicator of anything past that boundary, you need to be wearing PPE. The working distance is generally 18 inches. That's your arms. I've seen ones that are 22. Normally it's 18 inches. That is the full incident energy is at that working distance. But the chance of getting burned is anywhere from immediately at the source through the edge of that arc flash boundary. So that arc flash boundary is no one that's not qualified should cross that arc flash boundary when work is being done, and proper PPE needs to be worn from that point forward. So that's the reason that they give you the boundary, is that's the danger, you can get hurt. It's recoverable. The other thing to remember about wearing PPE is when you are in front of an event and something happens, that PPE rating that is recommended to wear does not guarantee that you will not be injured. What that PPE level gives you is curable injuries and curable burns. It does not mean that you necessarily would walk away not injured. So that's also a very important thing to remember, that 25 calorie suit that they're telling you to wear is like just going to make sure you don't have more than a 2nd-degree burn. Okay. So, and then remember that anything over 12 to 15 calories, you have the potential of impact injury. Okay. If the equipment starts to disintegrate. And then my last slide is sort of the takeaways. So when you're doing your hazard risk assessments, evaluating the condition of your equipment, evaluating that maintenance history to see, has this equipment really been maintained? If you're only maintaining stuff every 10 years, 8 to 10 years, know that your lubricants are not going to work like they were designed to do in the 3 to 5 years. That was what the manufacturer of both the switchgear and the lubricant recommended. Remember to review those arc flash labels for dates and potential hazards with the equipment that you're working on, and considering those changes in IEEE. And then always remember, distance is safety. The further we can get away from that arc flash event, when we're doing, our switching and what we need to do, be it whatever tool we use, whether we use a remote racking tool, a remote switching tool, a mimic panel, whatever the case should be, just remember that the further you get away from that arc flash potential, the safer you are. So any other questions? Hope I crammed it all in time.
Denise, I think that was great. I just want to point out that I do have another question coming in here. Let's see. This gentleman has 2 sites with high incidents. One of these sites had a power transformer 4 MVA, and the circuit breaker would clear the fault in 0.15 milliseconds. So we did different scenarios, and there's no way to reduce the incident energy below 9 cal other than changing the design, splitting the circuit into 2 smaller transformers, etc. I'm glad we bought the CBS ArcSafe remote disconnect.
Right.
Good
Right.
savings.
Yeah, anytime you can get out of that zone. My favorite device is our RRS3 MV2, our MagnaBlast racking tool. The scariest incident that ever happened to me in my career was on a MagnaBlast. And if I never have to stick my hand in a cell again and hold that clutch, it will be too soon. So, really evaluating your equipment and what your tasks are and what your staff has to do is super important. And then it's as important as maintaining your equipment. That's going to be the best way to have the safest system possible, the most reliable system, and the most consistent operation of your equipment is if you maintain it.